Okay, this is the third in my series of lessons on electricity. We've looked at Ohm's law, where the conductor is under constant physical conditions. We've looked at the filament lamp, where it isn't under constant physical conditions. The temperature is being allowed to rise dramatically. And I'm going to look at three more devices with you: the thermistor, the LDR, and the diode. And the thermistor is what it sounds like. It's a thermal resistor. The resistance decreases in contrast to the resistor. It decreases with temperature, and the decrease is many powers of 10. So your symbol for the thermistor looks like that, remember? Remembering to keep this parallel with this. If you plot the graph, or when you plot the graph of resistance against temperature, so there's resistance in thousands of ohms against temperature in degrees C. You'll start off up here maybe at some thousands of ohms. Let's say 2, 5, 10,000 ohms, and down here it'll maybe be 200 ohms. So if we said that was 0 degrees C and this is 100 degrees C, you've got a factor of 10 anyway in that 100 degree change in temperature. So that's your graph. You need to be able to sketch that graph. You need to recognize the graph as being for the thermistor. You can use it as a thermometer, so you can literally use it to measure temperature, because the resistance changes predictably with temperature. You can use it in a thermostat, which is not a thermometer. It's a thing that controls other things according to temperature. So you might have a thermostat. You will have a thermostat in your oven with your central heating, with your air conditioning in your car, for example. These all have thermostats so that you can set the temperature that you want. And they're also used to compensate for changes in resistance in circuits subject to large temperature variation. So if your electrical circuit is operating somewhere where the temperature changes a lot, like under the bonnet of a car, maybe just somewhere in the world where the temperature changes dramatically over the year. If you take Michigan, for example, in North America, the temperature in the winter might be minus 40, the temperature in the summer might be 30, so there's a temperature range of 70 degrees. The resistance in the circuit will change as a consequence of that change in temperature, and if you don't do something to compensate for that, your circuit will behave differently. So by putting the thermistor in as the temperature rises, as the air temperature rises, the resistance in the circuit will increase, but the resistance of the thermistor will decrease to compensate for that. So overall, the resistance stays the same. So that's your thermistor. That's what it does. That's its symbol. That's its graph. And that is how you might use it. The light-dependent resistor is my second device for this session. and this does pretty much what a thermistor does, but with light. So this is a device where the resistance changes massively. With light level. The symbol, you'll remember from my first lesson with you on this, is a resistor in a circle with light coming in. And if you sketch the graph for that, what you'd get would be resistance in thousands of ohms again, we'll say. And in the dark, we're maybe looking at 10,000 thousands, 10 million ohms. And in the light, we might be looking at maybe 200 ohms again. So there's bright light. And this is light level. Going this way. So, how am I to use it? Control circuits. Which operate according to light level. So, nightlights, for example. You might have had one of these when you were small. So when it gets dark, the light comes on so that it doesn't actually get dark in your room, lest you be scared of the dark. So they come on when it's dark. They are used to turn on and off streetlights. And if you look down from above on a streetlight, you would see that clear perspex dome on top, and underneath that there's an LDR that you can actually see. You might, for example, open and close your curtains. Don't know anyone that does, but you could open and close your curtains automatically. When it's dark. So that's your LDR. And the final device then that I need to talk about just now is the diode. And that only allows current to flow in one direction. Technically, a very small current flows the other way, but it has a very small resistance in the forward direction and a very large resistance in the reverse direction. Your symbol, you'll remember, is a triangle with a wire running through the middle, a bar on the apex of the triangle, and a circle around it. So the forward direction, this way, you have a very small resistance, so current is allowed to flow. In this direction, the reverse direction, you have a very large resistance, and so very little current flows, ideally none. So if you plotted your graph of current against potential difference for your diode, note the current is in milliamps in this direction, V in volts. Initially, there's 0. Initially nothing happens And then at about 0.7 volts, varies between diodes, but 0.7 is a typical value, it starts to conduct really easily. If you reverse the PD, nothing happens. But if you make it a big enough reverse PD, then actually the diode will break down and it will conduct. But this current is in microamps. This is in thousandths of amps. This is in millionths of amps. So these are prefixes, amongst others, that you need to know. So let me just remind you of those. If we go from the top, the biggest prefix, capital T is for tera, which is 10 to the 12, that's a million. Giga, capital G, is 10 to the 9, it's 1,000 times smaller, that's 1,000 million or a billion. Then you have mega, which is 10 to the 6, another 1,000 times smaller. Then you have kilo, small k, that's 1,000 times smaller. And then you have no prefix, so that could be terabytes, gigabytes, megabytes, kilobytes, and then just bytes if we're talking about computer memory size or transfer rates. Then you have, going the other way, milli, which we have up here, which is 10 to the minus 3, 1,000th. Then you have micro, which is 10 to the minus 6, which is millionth. And then you have nano, another one that you're probably familiar with, 10 to the minus 9. So you see they go in steps of thousands. This is 1,000 times smaller than this, which is 1,000 times smaller than this. Then you've got your no prefix. Then you've got 1,000 times bigger than no prefix, 1,000 times bigger than that, 1,000 times bigger than that, and 1,000 times bigger than that. So those are the prefixes that you need to know, right? So, how is your diode used? Well, it's used to protect delicate electronics. If you put your battery in the wrong way around to your clock radio, or if you could put your battery into your mobile phone the wrong way around, then it would destroy it. So in the possibility, or to guard against the possibility that could happen, there's a diode in the circuit, so if the battery does go in the wrong way around, nothing happens. No current flows because the diode stops it and protects the electronics. It's also used to convert alternating current to direct current. If you look at alternating current, we haven't done this yet, but why not? If you measured it against time, you'd see that sort of thing. So it's rising to a peak, falling to zero, and then it's rising to a peak in the opposite direction. So in a circuit, for example, if we had an AC supply across a resistor, then what you'd have would be, for this bit, the current's flowing in that direction. So let's do that. And for this bit, the current's flowing the other way. So it's changing direction. Now if you were to put that through your diode, then what you'd get out would look something like that. So you've lost this negative bit. Again, V in volts and T in seconds. So this turns AC into DC. That shouldn't be there. Okay, so you have a diode which is used to convert AC into DC. It's used to protect electronics. This is the graph you need to draw and be able to recognize as a diode graph. That's the symbol. There, sorry, I was off screen. There's your symbol for the diode. My apologies for being out of focus. That's what a diode does. That's why it does it, that resistance or change in resistance. Going back up, you have the LDR. That's what LDR stands for. That's what it does. The resistance is very low in bright light, very high in the dark. That's your symbol for it. That's how you might use it. That's the graph that you need to be able to sketch. Remember, kilo ohms, light level. There are units for light level, but we're not concerned about them. And this very large range of resistance. And then here, finally, or firstly, in terms of when I did it, the thermistor. That's what a thermistor does. That's the symbol for it. That's the graph for it. And that's how it's used. You need to know those three devices.